Let's have a look at another problem that looks a little bit different than some of the questions we've done to this point. It's really not that different, but it might seem different right now. We got two objects, A and B, that are connected by a light rope over a frictionless pulley. In other words, there's no forces that we have to worry about in here. There's no mass that we have to worry about in here. It's just the two objects that you see there, the 25 kilogram and the 35 kilogram object. We want to find, it says determine the motion of each object once the objects are released. Really what we want to do here is find the acceleration of the objects once they're released. Now, someone in the other class, we did this question yesterday actually with the other class, and somebody in the other class said, as we were analyzing this, finding the acceleration of the system, he said, well, don't you want to find the acceleration of each of the objects within the system? Hey, if the 35 kilogram object accelerates at 3 meters per second squared, then well, what rate is the 25 kilogram object going to accelerate at? Exact same rate, right? They go together. It's a system. Remember yesterday we talked about the semi-truck and the ice cream inside the semi-truck? They move together as one, usually at least. They move as one object. So if the semi-truck itself is moving, it's accelerating at 3 meters per second squared, then normally the ice cream within the semi-truck is also moving or accelerating at 3 meters per second squared. So we're not going to lose any sleep over that. We're not going to try to analyze these objects individually any more than we do any of the other questions that we've done. Let's look at the system, the 25 and the 35 kilogram mass completely. Now I'm going to ask you for this one question not to write down anything until I'm finished. Okay, you'll see why in a minute. Okay, just put down your pen, just use your brain here, look up in front of the room, pay attention to what I'm doing, and see if you can figure out as I'm going through this why I've asked you not to write down anything until we're finished. I promise I'll give you a chance to write it down once we're finished. All right, we got a 25 kilogram mass that experiences a force of gravity. I'm going to call that F1. Now, it's really Fg, but there's two forces of gravity acting on this. The force of gravity acting on the second object as well. So I can call it really whatever I want. I'm choosing to call it F1 and F2 just so that I understand that it's two separate forces of gravity that are acting. 25 kilograms pulling downwards, the 35 kilograms pulling downwards. 35 is bigger than the 25, correct? All right, let's get the values of both of those forces. F1 is going to be 25 times 9.81. F2 is going to be 35 times 9.81. What's the value of F1? What's 25 times 9.81? Thank you, 245.25 newtons. And what's the value of F2 here? 35 times 9.81. Right? Thank you. 343.35 newtons. All right, so far so good? Okay, now let's do what we usually do at this point, and that is to say that F net is equal to the sum of the forces. Remember, you're not writing anything down yet. F net is equal to, that's going to be F1 plus F2, the only two forces acting on this system. Now, there are forces acting in between. The rope is pulling on both of them, but we're looking for external forces here, right? We're not looking for the force of one ice cream pallet pushing on the next ice cream pallet. We're looking for the force that's acting on the truck itself, right? The external forces here right now. So we don't care about what's going on in between. We care about F1 and F2, the forces that are affecting the system itself. All right, F net is m times a. F1 plus F2. With me so far? What mass do we want to use there? We used M1 already, the 25 kilogram mass already in solving for F1. We used the 35 as well. What mass do we use here for this one? 25, 35, or both of them? Yes. No. Just add them together. This force is the force that acts directly on object number 1. This force acts directly on object number 2. This is the net force. The net force acts on the system. So let's calculate that based on the mass of the system. Look, the whole thing is accelerating. 60 kilograms is accelerating, so let's use the 60 kilogram mass there. F1 is 245.25, but it's what sign should it be? Positive or negative? Should be negative because it's acting down, right? What about the other force? F2, 343.35. But we're going to make it negative as well because it's acting down, right? Let's get these two forces combined, and then let's divide it by 60 kilograms. Negative 9.81 meters per second squared. That doesn't make sense, does it? Well, gravity is the only thing pushing down on it, yes. But should the system accelerate at 9.81? No, it shouldn't. There's a mistake here somewhere. That's why I asked you not to write it down. Okay, there's one simple, small mistake that we made on purpose to see if anybody would catch it. Now, nobody caught it when we made the mistake. Can anybody catch it now? Looking back on it, can anybody see what the mistake is? Yep.
Is it like, instead of it being negative 3.635, positive?
Good. Essentially, yeah. Yeah, good. Good, Nick. These two forces, although they're both acting down, right? They're both acting down. That's correct. They're both opposing each other. One is pulling the system like this. The other is pulling the system like this. They're opposing each other. So one of them's got to be a positive force. Now, Nick, it doesn't really matter which one is positive. You said that 345 is positive. 343 is positive. I'd probably go with that one as well. You'll see why I do that in a second. But it doesn't really matter as long as one is negative, one is positive. Here's what I like to do so that we don't get mixed up on that. You don't have to do this. Okay, you don't have to. But here's what I like to do to avoid that confusion. I like to pretend this is all straight on a horizontal surface like this. So basically what I'm doing is taking this 25 kilogram mass and then pulling it up like this. And the 35, I'm pulling it up like this. That means that if I do that, I'll have a force of gravity acting on number one that was 245.25, and a force of gravity acting on number two, which is 343.25. Does that make sense? Right? The forces of gravity are both really acting down. And I'm drawing one to the left and one to the right. It's not to the left and right. But you can see if I draw it to the left and right that I'm probably not going to forget to make one of these a positive value, like Nick said. If you can remember to do that and draw it the same way as we had it drawn before, that's fine. Okay, but this works for me. Straighten it out so we can visually see that one is positive and one is negative. All right? Let's recalculate this acceleration. It's not going to be 9.81. It's going to be something smaller than that, right? Because you got two forces that are opposing each other. It can't be 9.81 if they're acting against each other. Ben gets positive 1.6 meters per second squared. We're going to go with two digits, because if you look at this, this is two digits and two digits. Final answer should be two digits. It's positive 1.6 meters per second squared. We were actually asked to find the motion of both of them. That means that the 35 kilogram object will accelerate this way. The 25 kilogram object will accelerate this way. Okay, if you left it as just positive 1.6, I'd mark that correct. But in the end, they're both accelerating at 1.6, but one's accelerating upward, one's accelerating downward. Does that make sense? Okay, I want to do one more quick example with you here after I give you a chance to write that down, okay, which is same type of thing, but one small addition to it, and then we'll give you a chance to work on a couple questions. All right, let's have a look at this question, please. 3.11 on 156. We got two pulleys this time. We got two pails, same as we had last time, but this time it's over two pulleys. We got a mass in between this tire that has a mass of, what is the mass of this tire? 20 kilograms in between. Mass of pail B is 8 kilograms, and mass of pail C is 6 kilograms. Now we could draw it like this, But I like to draw it like this, where we have three objects all on a horizontal surface. First one being 8, second one being 20, third one being 6. We have a force of gravity that we're going to call FB to the left of 8 times 9.81. And we have a force of gravity acting to the right. We're going to call it FC, which is 6 times 9.81. This should be 58.86, and this one should be 78.48 newtons. Now, there is, strictly speaking, force of gravity and a normal force acting on the 20, on the thing in the middle here, right? But they cancel, so we'll ignore those. Leaves us with two forces. Let's analyze this system now. Let's say F net is equal to FB. That's the force of gravity acting on the first object, plus FC, the force of gravity acting on the second. MA is FB plus FC. What mass do I use here? 8, 20, 6, some sort of combination of them? Kai, what mass do I use there? The 8 and the 6? No. Here's what I want you to think of it as now, okay? Yesterday we used the analogy of the semi-truck carrying the ice cream. Okay, this is one semi-truck being pulled in two different directions. Now, we got 3 boxes of ice cream in that semi-truck. What are we going to use for the mass? Q? All of it, right? All of it. At this point, all of it, because we're looking for the net force. The total mass is going to be 34 kilograms times the acceleration equals FB, which is negative 78.48, plus FC, which is positive 58.86. Okay, 34 times A is equal to, I believe it's negative 19.62. And that's going to give me, I don't know, 0.5 something. Negative 0.577, or negative 0.58 meters per second squared. So we would say pail B accelerates downward, tire A accelerates to the left, and pail C would accelerate upward at 0.58 meters per second squared. Is that good? Got a couple questions for you here as you're writing this. Does the whole concept of straightening it out like this make sense? We don't have to do that, but I'm telling you, okay, I think you got a lot less chance of making a mistake on direction, positive, negative, if you do that, because you can clearly see that one is positive, one is negative here. Second question is, does it make sense why this is 34 kilograms? The total mass as opposed to just part of it? We use part of the mass in finding the force of gravity. We use the whole mass in finding the net force. That's always the way it's going to be. All right, we got a couple questions for you to work on here on page 157. Based on the example that we just did in 156, one little word of caution here, or at least a note. Question number 2, you make some changes to this system in question number 1. Then we're going to go back to the original, okay, the original diagram, and then make new changes to it in diagram 2. So the changes you make in diagram 1 or in question number 1 don't carry through to question 2. Does that make sense? It's a new question with the numbers from the diagram back the way they were in the example question. Okay, let's see what we can do with those 2 questions over the next few minutes here now. Let's try another example. This one looks even more different. This one's got a, well, in physics we call it an inclined plane. Really the simple term for that is a hill, but in physics we like to sound smart, so we'll call it an inclined plane. It's an inclined plane with an angle of 15 degrees, and it's got this box of 3.5 kilograms on the side of this hill. Now, in the absence of friction, we all know what's going to happen to this box, right? If there is no friction, this box is going to slide down the hill. What causes this box to slide down the hill? Forget about friction again for a second. We know it's there, but we'll deal with that later on. What causes the box to slide down the hill? Gravity. Gravity causes the box to slide down the hill, right? If gravity is the only force acting, however, besides friction, which we'll deal with later, then it wouldn't slide down the hill. It would slide straight down. It would fall straight down toward the center of the earth. So it can't just be gravity. Gravity's there, and we're going to call that Fg, same as we always do. But it's not the only force acting. What other force acts, Hugh? Good. The normal force acts. Normal force acts up like this. It's perpendicular to the surface, like this. Now, pay really close attention to what I'm about to do here. This normal force and the force of gravity combined give me this force. That force that I've just drawn, that resultant vector that I've just drawn, the combined normal force and gravity, is perpendicular to the normal force, but it's parallel to the surface. We're going to call it F parallel. And we're going to redraw it up here. Because in the end, remember what I said as we started drawing free body diagrams, it doesn't matter where you draw it, as long as you have it drawn in the right direction and the right length. So F parallel is the combined normal force and gravity. And F parallel is that force that pulls it down the hill. So part of the force that pulls it down the hill is gravity, but part of it is the X component of the normal force pulling it down the hill. Does that make some sense? Now, there's a couple of things you got to watch out for here. First of all, you have to draw that normal force the right length. Okay, what a lot of people will often do is diagram like this, draw the force of gravity acting down, and that's the easy one, force of gravity acting down. People will draw the normal force at 90 degrees, got to be 90 degrees to the surface, right? And then I'll draw this F parallel, this red force that I have drawn like this. That's wrong. And it's critical that you don't make that mistake. Okay, it's critical that you don't make that mistake, because if you do, you're going to end up using a wrong trig function to find the value of F parallel. Okay, that's the first mistake that people make. Okay, F parallel is not drawn horizontal. It's got to be drawn perpendicular to the normal force, and therefore parallel to the surface, because the normal force is perpendicular. Okay, the F parallel is perpendicular to it. Got to be parallel to the surface. Got that? Second thing is, we've got to recognize here that this angle in here, right here, will always be the same as the angle of the hill itself, 15 degrees. There are no exceptions to that. It has to be the same value. Why? Well, this is 15, this is 90. This would be 75. Well, this is 90 in here, so 75 plus 15 give me 90. This has to be 15 so that this is 90, and so that the interior angle inside this triangle there is going to be 180. Has to be the same angle. If you have trouble figuring that out using trigonometry or geometry, don't panic about that, because it's always the same. So draw your normal force perpendicular to the surface. Draw your force parallel, F parallel there in red. Draw it perpendicular to the normal force, and make sure the normal force is drawn the right length. Then redraw your normal force up here, and make sure you label that angle as well as 15 degrees or whatever it works out to be. Yep. Yep. Now let's draw the force of friction back in there. We're going to draw friction this way. I don't know what, yeah, I do know what the value of force of friction is. It's 3.9 newtons. Why have I drawn the force of friction smaller than F parallel? Do we know it's smaller? If it accelerates down the hill, then friction up the hill has got to be smaller, right? Okay, let's say F net is equal to the sum of the forces here. I'm saying F parallel plus FF. Any others? Zach, should I include FG and FN in here? It's a lot of forces. Should I include those? No, why not? Maybe? No, maybe? Anybody say yes? Hugh? Good, excellent. I'm not going to include Fn and Fg because I already have. The sum of them is F parallel. By putting F parallel in there, F parallel is not a force on its own, right? There's not some magical force that pulls something automatically down a hill. It is gravity and the normal force that we combine that pulls it down the hill. I'm simplifying it by getting F parallel. I could include Fn and Fg. I'm doing that in an easier way, though, by combining them before I have to write it into the equation. So we're going to put F parallel in there. We've already put Fn and Fg in there. We're not ignoring those. We're just not including them twice, that's all. The mass here is 3.5 kilograms. The acceleration is unknown. F parallel, we're going to make F parallel. Oh, we don't have its value, do we? We should find that. Let's look at that triangle again. We have the angle. We're looking for the opposite side. We have the hypotenuse, or at least we can find it easily. Let's say sine 15 degrees is equal to opposite over the hypotenuse. So let's say F parallel, I should say. I used to call it FH. Sometimes I still slip back to that. F parallel is equal to, we're going to say mg, 3.5 times 9.81 times sine 15 degrees. We get 8.886 for that. All right, so let's make it negative 8.886 because in the diagram we have it drawn to the left. And the force of friction, 3.9 newtons. So let's say, Adam, negative 8.886 plus 3.9. That's going to give me somewhere in the range of 5 divided by 3.5. Let's say 1.3. .4 meters per second squared. If we take a look at this, it's no different than what we've done up until this point, right? It's exactly the same. F net is equal to the sum of the forces. But we need to get F parallel. And how do we get F parallel? We get it by drawing this diagram correctly. Okay, we have to draw the normal force perpendicular to the surface, F parallel to the surface and perpendicular to the normal force, and then we have to analyze those vectors to get F parallel. Once we get that, again, we go back to here, and it's the easiest, well, I shouldn't say it's the easiest question, it's just as easy as the other questions for sure. Nick? Yes, yes. The force of gravity will always be the hypotenuse. But Nick, that's a good point. I'm glad you asked that question. If you drew this diagram wrong, okay, here's the hill, okay, there's the force of gravity, there's the normal force, and you drew the normal force too long, so that you drew it like this, you still made this 15 degrees. Then you would look at that and say, oh wait, force of gravity now is the adjacent side, and what you're looking for over here is the opposite side. So you'd end up using the tan function then, right? To find F parallel. You don't want to do that. Okay, we got to use the sine function to find F parallel. So yeah, you're right. Force of gravity is always the hypotenuse, and it's always the hypotenuse because we always draw the normal force in F parallel this way, not this way. You might think that you're not going to do that. Okay, I'm telling you, I would say numbers approaching half. Numbers approaching half as we go on in the days and you guys do a few more of these problems. Half of you, or almost half of you, will likely start drawing it wrong so that the F parallel isn't actually parallel to the surface, but rather is just horizontal. Don't do that. F parallel is called F parallel for a reason, because it's parallel to this. Okay, you recognize that, Nick? And you're always going to find that FG is the hypotenuse, yes. Let's try those two questions, please. Let's take a look at number 2, please. It says a 55 kilogram skier is accelerating down a 35-degree slope. So here's the slope, here's the skier, 35-degree slope here. We know the acceleration of the skier is 4.41 meters per second squared down the slope. Makes sense, right? He's skiing. He's not going to be accelerating up the slope. We have a force of kinetic friction. We know that force of friction is going to act this way because it has to act opposite to the way he moves, and he's moving down the slope. It tells me he's moving down the slope. Friction acts up the slope. Now, we also know that we have a force of gravity acting down that we call Fg. We have a normal force acting perpendicular to that surface, Fn, and we have a force of the hill, or F parallel as I like to call it, that's parallel to that hill, or perpendicular to that normal force. This angle right here is 35 degrees. Now, it's so critical that you draw this diagram. As I was walking around answering people's questions, helping people out, some people do the diagram, some people didn't. Some people draw the diagram wrong. Hey, I'd rather you draw the diagram wrong than not at all. Draw the picture. And when you draw the picture, try to remember that the normal force has to be short enough that F parallel can still be parallel to the surface, as opposed to like this, right? Told you guys before you're working on these problems, you want to make sure that F parallel isn't like this. It's got to be like this. All right, let's get the value of F parallel. We know that sine 35 is equal to opposite over hypotenuse. The opposite side of that triangle is F parallel. The adjacent, the hypotenuse is FG. So let's say F parallel is equal to FG, which is, what do we got here? 55 times 9.81 times sine 35 degrees. And what does that work out to be? It was 300 and something, wasn't it, Elizabeth? 309.473 newtons. Good. So there's FH. Let's label that now right here, or F parallel, I should say. We're allowed to do that. Right? We're allowed to move it as long as it's in the same direction and as long as it's the same length. We got a F parallel is 309.473 newtons. Now let's set this up as that F net is equal to the sum of the forces problem. Same as we have all those other problems. F parallel plus FF. Now, F net is M times A. It's going to be 55 times 55 times negative 4.41. Why negative? Because it's going down the hill. It's accelerating down the hill. F parallel, negative 309.473, and FF is what we're looking for here. 55 times negative 4.41, or what was that? 2. So we're going to say negative 242.55 equals negative 309.473. Let's take the 309 over by adding, and when we do that, I think we should get 66.9 newtons. And it's going to be a positive value, which tells me it's going to be up the hill, which we should have predicted that anyways, right? If it's moving down the hill, friction is going to act up that hill. Is that okay? Next question? No? We're good at that, guys? All right, I'm going to give you a worksheet here right now. It's a 4-pager. The good news is you can't do some of this yet. The good news is you can only do the first 3 pages to this point. Here's what I'd like you to do, please, for homework. I'd like you to do the first question on page 1. That's question number 1. I'd like you to do the second question on page 2. That's number 6. And then I'd like you to do the 5 questions on page 3. So that's going to be 10 to 14. That's 7 questions. It's quite a bit. Okay, but we also have about 13 or 14 minutes to get a good head start on now. Should be able to get a couple of those questions done, and then maybe be stuck with about 5 questions for homework tonight. All right?